We can now find rational zeros of a polynomial function. The problem, though, is that these zeros may or may not be actual zeros of a polynomial function. We have to check them using the remainder and factor theorem. So this is a problem with the existence of zeros. We now have a stronger theorem, though, the fundamental theorem of algebra, that tells us every polynomial function has complex zeros. Before we write this down, let me go ahead and note that rational numbers are a certain set of real numbers, and real numbers are always complex numbers. So a rational zero will always be actually a complex zero. Now let's go ahead and formally state the fundamental theorem of algebra. If f of x is a polynomial of degree n, which is greater than 0, and a is a non-zero real number, then f of x has exactly n linear factors and is equivalent to the following, where we have that c1, c2, and cn are all complex numbers. Therefore, this tells us that the c1s to c2s all the way up to cn are the zeros of our polynomial function, and they may have multiplicity higher than 1. Now, we're going to go ahead and find the zeros of the polynomial x cubed plus x squared plus x plus 1. And the first thing that we need to do is let's go ahead and find the rational zeros of this polynomial. So the rational zeros are going to be given by p divided by q, where p is the coefficient plus or minus 1, and q is the factors of the leading coefficient, which is still plus or minus 1. So all rational zeros are either going to be 1 or negative 1. To check this, let's go ahead and evaluate our polynomial function f of x, which will be set to be x cubed plus x squared plus x plus 1. Evaluate this at f of 1 and f of negative 1. So f of 1 is going to be equal to 1 plus 1 plus 1 plus 1. This is clearly not 0, so 1 is not a 0 by the factor and remainder theorem. Now evaluate f at negative 1, and this is going to be a negative 1 plus 1 minus 1 plus 1. Now this is 0, so negative 1 is a 0 of our polynomial. And this means that x plus 1 is a factor of f of x. Therefore, we can go ahead and take our factor x plus 1 and divide it into our polynomial here. So let's go ahead and start a new page. Now, using our polynomial division, we'll have x plus 1 dividing into x cubed plus x squared plus x plus 1. And we want to get rid of the x squared, so we're going to multiply our term x plus 1 by an x squared. This becomes x cubed plus x squared. Now adding this to the term above it, and we actually cancel out both terms, so we're just left with the 0 here, which means we can go ahead and bring down our x plus 1. And we want to get rid of the x, so we multiply it by 1. We get an x plus 1. Again, adding the two terms together, we get a 0. And what we see then is our x cubed plus x squared plus x plus 1 factors to be an x plus 1 times an x squared plus 1. Now, again, we're trying to find the zeros of this polynomial here. So we can go ahead and do this. We'll set x squared plus 1 equal to 0. Subtract 1 from both sides. We'll get an x squared is equal to a negative 1. Then go ahead and take the square root. This is going to give us x is equal to the square root with a plus or minus in front of a negative 1. So x is equal to plus or minus I. These are the complex zeros of our polynomial, and we already found the real zero, which is x is equal to negative 1. Now let's review a definition for complex numbers. If a plus bi is a complex number, then a minus bi is called the complex conjugate. Now, the interesting thing about complex zeros and their complex conjugates is that they always come in pairs for zeros of a polynomial function. So if f has a complex zero of the form a plus bi, where f of x is a polynomial function, then the complex conjugate a minus bi is also a 0. In this last problem, we're going to construct a polynomial with zeros 3 plus I and 4. This means that if 3 plus I is a zero of our polynomial, then the linear term, 3 minus our 3 plus I, is going to divide our polynomial. And by the previous statement, the complex conjugate will also be a zero. So another linear term our polynomial is going to have is an x minus 3 minus I, where this complex number is the complex conjugate of this complex number. And finally, we also know another linear term, x minus 4, needs to divide into our polynomial since we're given the last zero was 4. This means one polynomial that meets this criteria would be given by x minus 4 times an x minus 3 plus I times an x minus a 3 minus I. And this would be one example of a solution.